Well, today's class is about distance between 2 points and the Pythagorean formula. Let's say that we have a map like this one and we want to know the distance between two cities such as Tijuana and Cabo San Lucas. Now you may be asking me, teacher, we can do that with a web application or something on my phone, but you know what? We gotta learn what's the principle behind your phone and how does technology work, which is something that everyone has for granted today, but it's based on a math principle. And that's why we're going to see today what's behind those programs that have these capacities. So how do they work? Well, before we can get the distance, we have to locate them, and we're going to use coordinates. For example, Tijuana has these coordinates. These are the approximate coordinates for some position in Tijuana, and Cabo San Lucas has this other set of coordinates, which are going to be about this. These numbers are very similar to what we understand as the x and y coordinates that we handle already in the classroom. For example, this is going to be the x and this is going to be the y, north, and this is west, west and north. Okay, and it's based on the following idea. This is the Earth, and there's an imaginary line called a prime meridian, which passes through the Greenwich city in England, and everything that is behind this we call it the west, and this is going to be the east. Everything that is relative to this, we're going to get a number. For example, this amount, so this is going to be 117.11 degrees to the west, so it's 117 to the west, and this 32.52 north means that you have 32 degrees going up from the equator, which is not shown here. But the equator, it's also an imaginary line that passes through Ecuador, and it's pretty much the half of the Earth. Passes right there through the half of it. And let's say then, what's going to be the distance? Now, let's also take into mind that it's not going to be the distance that we travel when we are on the road, or the distance that, I don't know, some other distance. For example, if you take some transport, like a bus, it's not going to be maybe, I don't know, well, it depends, right? Well, the distance that I'm talking about right here is if you would take an airplane from here to here, and it would be the shortest distance between 2 points. That would be a straight line. What would be the straight line distance between those 2 points? And to do that, we need to go back in time to a city called Samos in Greece, the island of Samos. I don't know. And in there we have back then, guys, there was a philosopher mathematician known as Pythagoras. And one day he was playing with some triangles, and he found out the following. He found out that, well, let's imagine that we have these triangles and we place some squares. Of course, everyone remembers what's a square, right? All the sides are exactly the same, and this is also the same for the other shapes that we have here. So this is a triangle. I'm sorry, this is a square, and here's another square, and he placed them exactly on each side of this triangle. And this triangle isn't just any triangle, it's a right triangle. So let's take these squares and put some grids on them so that we can see how many square meters we have in them. So let's imagine that each grid that we have here, each little square that appears in this grid, is going to be a square meter. So let's say that we have in the first one 9 square meters, and on the second one we have 16 square meters, and on the last one we have 25 square meters. and these belong to this original setting that we had before. Now, what do you see between these numbers? Do you see a pattern? Do you see a relationship? For example, 25, it's very related to 9 and 16. Do you see now what it is? Well, it's going to be the addition. When you add 9 and 16, you get 25. Alright, so that's pretty odd, right? I mean, how can this square be related to these other squares? Well, Pythagoras found out what it was. It was the area. Because, for example, we have here a side of 3 meters, and also this is 3 meters, 4 meters and 4 meters, 5 meters and 5 meters. When you multiply these sides, 5 times 5, you get 25. That's why we have 25 little squares here. And over here you have 16 little squares. And to get that, you got to multiply 4 times 4. And this one is going to be, of course, 3 times 3 to get the 9. Okay, so this is going to be the equation for the Pythagorean theorem. But this is not really appropriate because not all squares have a side of 4, 3, and 5. Of course, that's why we have to generalize this in the following way. Instead of placing 4, 3, and 5, we're going to use A, B, and C. And this C, of course, is going to belong to the longest side, and AB is going to belong to the shorter sides of our right triangle. And why do we have the Pythagorean theorem? What's going to be the purpose, or why should we use it? Well, it's going to be for getting one of the sides. For example, what if we don't know the longest side of our right triangle? And of course it has to be a right triangle. If it's something else, if it's an isosceles, if it's a scalene triangle, it's not going to work. It has to be a right triangle. And you have to remember that a right triangle, one of its characteristics is that one of its angles is going to be 90 degrees. So this is going to be the 90-degree angle, and always the longest side, it's going to be in front of this 90-degree angle. Then what's next? Well, of course, let's say we have a problem like this one. We know that this side is going to be 4 meters. We have this one to be 3 meters, and we don't know the side of this one. We know this one already. I mean, we did this already, but I'm just going to walk you through a problem, and I'm going to show you the logic behind the solution to one of these problems. When you know one of these two sides and you want to know the longest side of your right triangle. So of course we know, thanks to Pythagoras, that on each of the sides we can make a square, and all of the sides, I mean each side of our triangle is going to have its own square, and this has a square, and you know that we know that this side is 4 meters, so when you put your square there, the square has to be a 4 times 4. That's going to become 16 square meters. This one is going to be of 3 meters, so of course this area of this imaginary square that we placed right there is going to be 9 square meters. And what's going to be next? Well, we figure out that through Pythagoras, we know that this square that we still don't know yet, although we do, but imagine that we don't, when you add these two squares, the amount that you get is going to be exactly the same as the area of this guy. And of course, we know that it's 25 for this case. And what's going to be next? Well, we know that this is going to be the area. It's 25. Now the question is, we don't care about the area of this imaginary square. We want to know the length of this side of the triangle. So what do you have to do? You got to get the square root of this square in order to get the length of the square, because that side of the square is going to be exactly the same as the unknown side of our triangle. And in this case it was 5. Therefore, the unknown side is going to be also 5 meters, which is the length of this square. Now let's go to something that we need to know. It's the terminology of the triangle for the Pythagorean theorem. So we have here these two sides. They're the shorter sides compared to this side. This side is the longest side, as you can see, and it has a special name. It's the hypotenuse. Hypotenuse, guys. We're gonna use that name. That hypotenuse, it's always in front of the 90-degree angle. You gotta remember that. It's the longest side, and it's the side that is in front of the 90-degree angle. And we also have the shorter sides, which have a weird or funny name. They're legs. These are the legs of the right triangle. Guys, that's how it's called. I'm not kidding you guys. That's the way it is. So let's move on. Okay, we're gonna call them legs, and this is the hypotenuse. Okay, example problem. Let's say that we have this right triangle, and we know that this is a side of 6 meters and this is a side of 7 meters. What is the length of this side? That is the big question. How much is that going to be? Well, we have a right triangle and we can apply the Pythagorean theorem. If it wasn't a right triangle, too bad, sorry. Let's skip the problem. We can't do it, but it's a right triangle, so we can solve this. Oh, okay, if it would have been something else, you can't do it directly. You would have to do some modifications. If you have an isosceles triangle, yeah, you can do it, but it wouldn't be directly as we did here. We could do like the isosceles triangle should be cut into two parts, where each part it's a right triangle. But don't worry about that. We're not gonna see it very soon. So let's continue with this problem. Alright, so we're gonna use the Pythagorean theorem for this case, and of course we have our formula there. We have the two legs, the shorter sides of our right triangle, and we have the hypotenuse, which is what we're looking for. And what do? We gotta substitute these values into our Pythagorean theorem equation. Now you may be asking yourselves, which one is A and which one is B? Well, it works the same. If you choose this one to be A and this one to be B, it's all the same, because when you add them, when you add this one plus this one, or you add them in the other order, it's gonna give you the same thing. But you can't confuse the A or B with the C, because the C is the hypotenuse. It's not one of the legs. The legs, you can interchange them, but the hypotenuse, nope, can't confuse them with these guys, because this guy is on the other side, and no, it's not the same. A and B can be interchanged, but can be interchanged the B with the C or the C with the A. Alright, so anyways, we gotta change the A for, I choose the 6 to be the A. I could have chosen the 7 for the A, but it's all the same as I said. So I had the B here to be 7, there you go. And what's gonna be next? Of course, I gotta get the square of each of the numbers. So it's 6 to the power of 2 is gonna be 36, and 7 to the power of 2 is gonna be 49. That's gonna be this part of the result. I gotta add them and I get 85. But this is not yet the answer, because this is x to the power of 2. I gotta get x by itself. That means that I have to get the square root of both sides. And when you put a square root on a square, it cancels out and you get this x. And then you gotta get the square root of 85, which is this. Let's do the prime division method to get the result. So when I do prime division, I realize that I just get these two prime numbers as the factors. And you know that's going to be a problem, because I told you how to get the square root when you have pairs. But here there are no pairs, so that means that the result is going to be prime, and it's going to be a prime root. And what do? Well, if you give me the answer with this square root of 85, it's going to be correct. It's going to be a check. It's going to be great job. But if you give me the answer in decimal, that's going to tell me that you used a calculator or some other application that you can find on the web. I don't know. Or maybe you copied it from some, I don't know. But the point of this, well, of what I'm telling you right now is that if you get something like this, don't bother getting the decimal result. Just give me this, because I know that you're supposed to not be using the calculator. So if you just give me this, I'm gonna be happy. That's gonna be it. That's your answer. You're done. Okay, so use the prime division method. If it's not possible, leave it as a square root. Moral of the story. Let's continue. All right, let's see this other problem of a Pythagorean equation problem where we know now this side. What do we call this side, guys? What do we call it? Oh, that's right, it's the hypotenuse. And this one is the leg. And this one, the unknown, we're looking for the length of this leg. How much is that going to be? Well, again, we're going to use the Pythagorean equation, Pythagorean theorem equation, because this is a right triangle, so I can apply it. Well, what do we do here? We know the legs. You know that the square of this side plus the square of this side is the same as the square placed on the hypotenuse, which is this case, which is this, okay? So now we gotta substitute the x not on the c. Now I'm gonna substitute it on the a or the b. So I chose this one to be a, but as I said before, a and b can be interchanged. It's the same deal. What's gonna be next? I gotta get the squares of each, and I get 6 squared is 36, 10 to the power of 2 is 100. What else? What else do we have here? Well, now we gotta do some algebra. This is being added. What is the opposite of addition? Everyone says subtraction. That's right. So we get 100 minus 36. I need some more space. I need some more leg room. 100 minus 36 is 64. And what's going to be next? I got to do some algebra as well. That means that I got to do the opposite of a square, and the opposite of a square is going to be the square root. So remember, when we have an addition and I want to clear that thing, it has to be a subtraction. When I have a square, the opposite of squaring is going to be doing square root. Alright, so this is like the same principle of algebra. What's going to be the answer here? What's the square root of 64? Two numbers that when you multiply give you 64. Now, I could do the prime division method, but I think this one is pretty easy because everyone knows that 8 times 8 is 64, right? And that's going to be the answer. Now, you may be asking me, or somebody could be asking me, but what does this have to do with finding the distance between 2 points? Well, I'm glad you asked. Let's see what we have here. We have a Cartesian plane, and on this plane we have something that you may be very familiar with. We have a rascal right there. And that rascal is very hungry. He wants to eat some fried chicken right there. Now the question is, what is the distance between the rascal and the chicken? Fried chicken, actually. Well, that's the big question we gotta figure out before we do all of the procedure. We have to know the location of our points of the rascal and the chicken. The chicken leg, actually. And what do we have here? Well, it's going to be the rascal has 2, 2 because we have the first number. Let's remember, guys, what coordinates represent. The first one represents the distance that is horizontal, and the second one represents the distance that is vertical, that is the height. And this other point, it says 6 comma 5 because you gotta move 6 points or 6 meters or whatever we have here in the units, and then 5 units up. That's what this coordinate is telling us. What's next? What do we do? What do we do? Well, okay, let's imagine, guys, just for kicks, that I'm gonna place here a line that is vertical, of course, and it's totally parallel to this length. What do we do? This side is totally parallel to this. Okay, why? You're gonna see in a moment. You're gonna see in due time. Okay, so we place this line that goes exactly from here to here, and it tells us something like the height of our chicken, fried chicken. How much is this gonna be measuring? Do you know? Can you see it? Can you figure it out? The height here is 5. The height of the chicken is 5. The height of the rascal is 2. So what's gonna be this height? Did you guess it? Did you? It's 3 meters, right? Of course you did guess it. Now what about this length? What is the length between the rascal and the chicken? What's the horizontal distance? Okay, what's gonna be this amount? Do you know what it is? We got from here to here it's 6 meters, and from here to here it's 2 meters. So the distance between these two imaginary points is gonna be 4. This is 4. This is 3. And guess what we just formed? What is this? It's a right triangle. This is great because now we can apply our knowledge of the Pythagorean Theorem to solve this, and this is great. Okay, so what do we have here? We have again the same formula, a plus b equals c squared, and we gotta substitute it into these values, 3 and 4. 4 squared. Guys, you know this answer, right? This is familiar to you. You guys know how to get this. You know it's 5. The answer then, the distance between these 2 points is gonna be 5. That's what we got right there. We're done. Now, this is for this case, but what if we want to do it for any point on the Cartesian plane? What do we do? Well, how do we get these two numbers, the 4 and the 3? That's going to be very basic. So instead of placing the 2 and the 2 and the 6 and the 5, I'm going to place x1, comma y1, x2, comma y2. So this is going to be 0.2 and this is going to be 0.1. I could have called this one x1 and y1 and this one x2 and y2, but I didn't. Why? Because it's all relative. You can choose, you can pick which one you want to be x1 and y1, which one to be x2 and y2. But very important, you can't combine the numbers. I mean, you can't say, oh, this is x1 and this is y2, or this is x2 and this is y1, or this is x1 and this is y2. No, you can't combine the numbers because they belong to a point. It's like you can place 2 people in different positions and they're still the same people, right? But if you exchange their last names and their first names between the 2 people, that's gonna be weird. That's representing not the same people anymore. Something like that happens also over here. Okay, anyways, this 3, how do we get it? It was doing 5 minus 2, right? So we have to get the subtraction of the y's. That's why instead of placing 3 there, I'm going to do y2 minus y1. It's going to be this amount. I put parentheses there just because, but we don't need to do that because it's not a coordinate. So I don't know. I can erase them if you want. Okay, I'll do that. Also here, I'm going to erase it because maybe you can get confused. You can think that it's going to be another coordinate. It's not a coordinate, okay? It's a distance. You got to get the distance between the y2 and the y1. You got to subtract them to get this distance. And then we got to get the distance between these 2 points, the horizontal distance, and it's going to be x2 minus x1, which is what we did here to get the 4. We did 6 minus 2, and it's 4. And we do it in a more generalized form as x2 minus x1. What's going to be next? Well, of course, as we did before, we got to substitute this information into our equation of the Pythagorean Theorem. And we have here, let's say, we have c squared equals a squared plus b squared. The a is going to be one of the legs, which is this one. The b is going to be one of the sides, one of the legs, as this one. And c, of course, is going to be our hypotenuse. And here, the length of the leg, it's now going to be x2 minus x1, well, this leg, there you go. And this side, this length is going to be y2 minus y1. Okay, that's how you got the length of this imaginary triangle that you had to form in order to get the distance between those 2 points. And then of course you have c to the power of 2. You don't want c squared. You don't want to get the area of the imaginary square that is formed here. What you want to get is the length. So that's why you got to get the square root. That's what I did right here. And just to make things more clear, instead of using the c now, I'm going to change it into a d. So this equation, even though it looks kind of weird, kind of crazy, kind of strange and complicated, it's not that complicated. It's just the same old Pythagorean theorem equation, cleared for the hypotenuse and placing the length of these imaginary values when you have these coordinates. Alrighty, so this is going to be the equation we will be using to get the distance. So let's say, for example, that we want to solve finally this problem. How do we get the distance between these 2 cities with these coordinates? What do we do? Well, I'm going to use this equation. And to make things more simple, instead of using those decimals, I'm going to change them to just the rounding off of those numbers. I'm just going to take away the decimals. They're not really rounded because this is 32.52. I should have placed it as 33, but I just took away all the decimals because it's just an example, okay? I'm going to get the distance between these 2 points, and I'm going to call them however I want, but I'm going to call this one x1, y1, and this is going to be x2 and y2 because I'm going to call this point 2 and this is going to be point 1. I could have picked this one to be point 2 and this one to be point 1, but I didn't, because I'm going to show you something else that you need to see. But if you would have done it in the other way, it would have been the same result. The result will be exactly the same. Why? Because we're going to see right now. Okay, so let's see here. We have x2 minus x1. x2 is this guy, and I'm going to subtract it from x1, which is this guy. Okay, so that's why I have this. And then I gotta subtract y2 minus y1. This is y2. This is y1. Gotta subtract them. 22 minus 32. What do we get? Well, you gotta respect the signs, guys. This minus this is gonna be negative 8. And this minus this is gonna be negative 10. Very careful, guys. When you get the square of a negative, negative times negative will give you what? I don't hear you. I don't hear you. That's it. It's positive. Very good. You got it. So negative 8 to the power of 2 is going to be positive 64. Negative 10 to the power of 2, you know, of course, that is positive 100. Now, guys, this is what I wanted to show you. If I would have picked this one to be x1 and y1, if I would have done it backwards, if I would have done this one like over here, or I don't know. If I would have set this one to be x1 and this is y1, this is x2 and this is y2, and I subtract this 117 minus 109, that would have been a positive 8. And if I would have done this 32 minus 22, instead of the order that I placed here, it would have been positive 10. But when you square them, you get the same result. So that's the proof that shows you that the order doesn't matter which one you pick to be P1 or P2, because if you change it in the order, it's going to give you a different sign. But once you square it, that sign disappears. You get the same result. Even though this one is negative or positive, you always get it positive after you square it. Then you gotta do, well, okay, well, we're done with that discussion. Let's continue. We're gonna continue with this problem. Let's add 64 and 100. It's 164. Then after that, we gotta get the square root. You gotta do the prime division method, guys. Or in this case, for kicks, just to show you the exact result, you shouldn't do the decimal result, okay? I just did it here. I did use the calculator in this case, but it's just for a purpose. It's to show you the length that we get. So 12.86, that's not the length, that's not the distance between those two big cities. Alright, it's not 12 meters, it's not that. We gotta go back to our definition of a degree. We gotta do some physics here, guys. We gotta do physics. 1 degree is the same as 100,000 meters. Now this definition, it's gonna vary depending on where you are. For example, if you are closer to the North Pole, 1 degree is going to be shorter. It's gonna be smaller. And the closer you get to the equator, the degree is going to be bigger, because it depends on the globe. The degrees change depending on the globe, okay guys? But that's another discussion, so I'm just going to leave it off to say that 1 degree is approximately 100,000 meters. But this varies, I gotta say it. I wouldn't be doing my job correctly if I didn't tell you this. Just gotta tell you guys that 1 degree changes, or the degrees change depending on where you are. So that's what you have on the globe, okay? Alright, so if we take 1 degree to be 100,000 meters, which is a very good approximation for what you have near Mexico, 100,000, and the result that I got here is going to be also in degrees, because these amounts are in degrees. And I got to multiply that by this, 100,000 times this, and it's going to give us this amount, 1,286,000 meters. But to make it more comprehensible, I'm going to change that to kilometers, which is 1,286 kilometers. And this is just using the Pythagorean Theorem. And also, guys, we're going to use one of those internet applications, internet web pages that can tell you the distance. And I used it to prove that this is fairly accurate. The procedure that we did through the Pythagorean Theorem and our approximation, it's pretty accurate. I mean, come on, you get a distance of 1,279 kilometers in the airline route, which is the route that you have right here on a straight line. 1,279, pretty much the same as 1,286, which is what we got here. And I also eliminated the decimals. If I would have placed them, could have been a lot better, but nope, I did not do that, because that would take up more space. But this approximation was pretty good. It's pretty much the same as what you have in the actual maps, 1,279. So that's the actual distance. Now, of course, the maps, they use something a little bit more complicated because that equation that I gave you, that's for when you have a plane. I mean, yeah, plane, you know what a plane is, right? Like when there's no curvature. And when there is curvature, you gotta use something a little bit more complicated. You gotta use more equations that take into account the radius of the Earth and its curvature, and that's how they got this amount. But when they're pretty short amounts, pretty short distances, we can approximate the length on these 2 points on the globe to be pretty much a straight line. And that's the idea of what's behind many of the technologies that you guys use for granted every day. For example, if you're lost somewhere and you want to find an address or someplace, maybe you want to know what's a great restaurant to visit. You use Google Maps and you get the address. Well, Google Maps uses an equation like these and also these other equations, Pythagorean Theorem, to get the distance between where you are and where you want to be. Many times those applications, they tell you, oh, this restaurant is 3 kilometers away from you. Or also it can show you suggestions of what's around you. And again, this information is based on the Pythagorean theorem. And this is based on satellite information with the coordinates, which is also used on this other very popular application called Uber. And this is going to be, I mean, getting the distance, you can agree totally that it's used a lot in the Uber application, for example, to know which is the closest driver around you, or maybe how much time it's going to take you to be in some place. That information, it's basically found through the Pythagorean theorem and of course more equations, but it's based on those principles. All of this thanks to Pythagoras and his principle. Alright guys, well, you have a great day.